Okay. So, hello everyone and welcome to this, let's call it workshop. I'm not sure if it is a workshop, but today I'm going to show you how you can work with high performance computing environments, especially using this CSC available here in Finland that you can use like in general and for the homework assignments of the course and things like that. So this presentation is a part of the class. And also like for other people that would like to know how to work with these machines. All right, so I have some slides to show you. So with this format, so I'm not going to go through like full screen. And then we're going to have some hands-on experience how to work with kind of machines. Okay. So if I can find my mouse cursor, is it there? Okay. All right, so I'm going to have a short introduction about the general like HPC or high performance computing environments and the CSC. Then we talk about the accounts and the projects that you can have on CSC and how you can connect to it, how you can log in into computer clusters. Then we talk about the module system, batch queues, and interactive views. And after this, we're going to have some experiments with the system. Okay. So before talking about CSC environment, you should know some terminologies in HPC environments. So the first one is called node. So basically a node is So a node is a single computer in a HPC cluster, right? So it's a single server. So a node can have a bunch of CPU cores, can have like a bunch of memory blocks, and it might have a storage system also as well. And if your node, if a node only has CPUs, we call it a CPU node. If it has CPU and also GPUs, we call it GPU nodes. Based on the definition of node, you can define a system called a computer cluster. And basically, a computer cluster has a lot of nodes in it. You can divide the nodes between the login nodes and the compute nodes. The login nodes are responsible for managing the compute nodes. So usually when you log into the system, you log into one of these login nodes. The hardware are not like very advanced. You don't have a lot of CPUs and GPUs in the login nodes, but you can only use it for like temporary files, small applications like debugging, these kind of things. But the important part for the login node is that you can submit your jobs that can be executed on these compute nodes. And how in HPC environment is done, it's usually done based on a job scheduler or a queuing system, which in the case of the CSC system that I'm talking about, the software that manages all of these things is called a Slurm, which stands for Simple Linux Utility Resource Management or something like that. Yes. And so the workflow is you log into the login node, right? You write your something called batch scripts, and batch scripts defines your jobs that you want to compute, that you want to execute on these compute nodes, and then you submit it to the queue using this Slurm utility, okay? And we see how it is done today. Apart from the login nodes and the compute nodes, you have a distributed database system or distributed storage. In CSC, they call it Lustre. And when you log into a login node, then you get some storage in Lustre with different partitions that we're going to briefly talk about. Is that clear, these things? Okay, so CSC is an IT service provider in Finland. It provides different services. You can like categorize the services between like supercomputers or computer clusters, that as I defined like before, and also some cloud services for storage, these kind of things. So we don't talk about the cloud services, so we focus on these supercomputers. So basically, it has 3 supercomputers available at the moment. The first one is called Puhti, which is a general purpose parallel computer. You can run any kind of code on Puhti. Next one is Mahti, which is optimized for massively parallel tasks like data parallel programs. And the next one is Lumi, which is one of the biggest in the world. I think according to top 500 website, it's now the 8th fastest computer in the world. So Puhti and Mahti are national supercomputers, but Lumi is in European scale. So today we don't talk about all of them. We focus on Mahti, but the way you work with Mahti is quite similar than Puhti and Lumi. So if you know how to work with Mahti, then you know how to work with others. All right, so let's see what Mahti provides in terms of hardware. So as I mentioned, it's suitable for massively parallel jobs. It has 1,404 AMD ROM CPU nodes, which means that you have like this number of like physical computers in the system. Each node has 264 core CPUs, and each core has 2 hardware threads. So typically in a node, you have 256 cores that you can run in parallel, right? 128 you can run like in parallel, and the others you can use for latency mitigation, as we talked about in the class. So each core works with this 2.6 gigahertz base frequency, and in each node you have 256 gigabytes of memory. So if you compute the number of cores, then you'll see you have about 180,000 cores roughly available on this machine. Apart from the CPU nodes, you have 24 GPU nodes. Each of these GPU nodes have 4 NVIDIA 800 GPUs. So you have 4 GPU per GPU node. And you have 40 gigabytes of memory per GPU, right? And then in total, you have 512 gigabytes of memory, like this, the host memory for the system's memory, and 3.8 terabytes of disk drive. Okay. Something that you should know here is like this configuration is slightly different for Puhti. And the big difference is the software stack that is installed on these machines. So on Mahti, you have like some software that is pre-installed for you, but Puhti has a lot more software utilities that you can work with. So it depends really on what is your application. And for getting the list of all scientific software available on these machines, we can visit this link. Any questions? You can stop me anytime you want with my presentation. All right. So it was a very brief introduction of CSC. So let's see how you can actually use the system. So the first thing that you need to do is to create a CSC account. So I created a project, and it sent you an invitation link, I think, a month ago. So you can use that link to join a project, or you can use this link to join a test project that I created for this workshop today, that you can see here. So with an account, with a CSC account, you're going to be able to create a project or join like an available project. So if you are a professor or a research or a PhD student, you can create your own projects. Otherwise, if you are a Bachelor of Master's student, you should ask your supervisor or I don't know, teacher to create a project and add you in that. So that's what I did for the class. So anyone also online, if you want to join this project for this workshop, you should use this invitation link that I provided in the slide, but you don't get immediate access to the services. It might take around 30 minutes for the service to be available for you. Okay.
Yeah, sorry for the inconvenience.
Sorry?
It was linking the Zoom.
Yes, for sure. Yeah.
Okay.
All right.
It's yeah.
Let me see. So I provide the link here. So if you want to join, you can join, but not this one. It's let me do it another way.
Right.
All right, so you should get it now. For the students of the class, you should already have access to this
Parallel programming, Åbo Akademi University.
but for this workshop, you can also use this link. Okay, where it was here. All right. So if you have an account, then you can create a project and then or join a project. So in each project, you can use different services, right? So if you have a project, then you can request for services per project. So if you open the project, you get some information about the project, like the project number, which is very important. The billing unit, which is the unit that allows you, like how long you can use the system based on the resources, the name of the project and things like that. But the important part is the services subsection, which tells you what services, what supercomputers you can use. So for this project, for example, I added two services, Mahti and Puhti. Then, depending on the service, you should also separately log in into the service with your CSC account that you have already available. But note that after April, Puhti and Mahti are using two-factor authentication method. So you should also have this authenticator app available on your phone to be able to log in. Okay, so I'm not going to go into more details about these logins because CSC has a very good documentation. You can follow things up quite easily. All right, so now assume you have an account and you join the project. So let's see how we can connect to the computer cluster, to connect to the login node. Basically, using CSC in general and Mahti and other services, you have two ways for connecting to the login node. You can connect through a web interface that is provided by the system and also an SSH client. So for the SSH client, you can also visit this link for general setup. I would recommend you to if you use Mac and Linux, that's fine. But for Windows users, I recommend you to use this WSL or Windows system, Linux system in Windows. Otherwise, you should use other software for Windows, like Putty. So, like if you want to work interactively in the class, you should also create your SSH keys and add it into your user, which is quite easy.
Sorry, find the link.
I put it in the Zoom link.
Can you send it again, please, to the Zoom?
Yes. So after you set up your SSH keys, after you set up your SSH keys, you can log into the system on Linux or Mac or WSL2 shell using this SSH, your username that you can see on your account, and then Mahti, Puhti, or Lumi at .csc.feed. Then you log into the system. Okay. So I will show you in a minute how you can really connect and what are these web interfaces that is provided here. Okay, so this is a screenshot of the web interface. So if you log in into the system successfully, you get these interfaces. So the home directory is for the storage and other things. And these are not quite important at the moment. So you have this compute node shell, you have login node shell, which is a web shell that you can use. Then it also gives you a complete desktop with GUI and everything. You can get a Jupyter notebook for Python. Then you can get Julia, you can get TensorBoard, and also a web version of Visual Studio Code. I personally recommend you to use the SSH because it's going to be quite helpful when you are developing applications, and it is quite good for debugging purposes. Then you can connect it easily to your local VS Code. That's going to be helpful for managing files and like GitHub and things like that. I usually myself use this web interface just for testing purposes, not for serious applications.
Agile project.
Yes, I will do that. All right, so now I think these were the slides that I wanted to show you. So let's see how we can actually work with this.
From the Jupyter, for example, if I want to use Jupyter in the web interface, from there I can also have access to like GPU and so on.
Yes, you can. Yes.
For like testing purposes.
Yep. Yes, you can, but the resources that you can request is limited. So if you want to access to the GPU, I will talk about that later, but it doesn't give you the whole GPU. It gives you a portion of GPU.
Oh.
Okay. It might sound strange, but in NVIDIA, in like 300 and 800 GPUs, has a technology called MIC. I forgot the abbreviation, but this MIC thing allows you to divide the GPU into 7 portions, right? And then this interactive sessions like in Jupyter gives you only 1 portion of that GPU. All right, any other questions? Okay, so first let me see my checklist here. Okay, so first let me show you how you can get access to this web interface. I can find it here.
Means multi-instance.
What?
Multi-instance.
Multi-instance GPU, yes. All right, so if you open this link my.csc.fin, you get this authentication page that then you can use Haka, for example, to log in with your account. All right, then you can see your project. So here I'm seeing some requests. So this is your dashboard. So if you go to the projects, you see your projects if it opens. Okay. So currently I have 3 projects here, right? So let me just add you. Okay. So now you are added in the project, but it might take like about half an hour to get access to Mahti input. All right, so this one as well. Okay, so from now on I work with this project. So, but for the course, for example, you can use the project created for the course. All right. So in the services, you see Mahti and Puhti. So if you use this login button, then you need to log in into Mahti, right? And here you can see some status about the current usage of the system. When you log in, you should use your Haka again, and then you need this 2-factor authentication thing after that. So it's called MFA code that you should use your. Authenticator app. Okay, so now I am connecting to the system. So you can see the web interface that I showed you in the slides, right? So in the beginning, I'm going to show you how you can use Jupyter with GUI, with GPU for Python and or PyTorch applications. So if you click on this Jupyter here, you can get some information. So for example, here, you have to choose the project that you want to use this Jupyter notebook in. So I use this, yep. And then it is something called the partition. So basically, partition is something that is defined by the queuing system, in this case, a Slurm. And a partition is a logical set of nodes that are defined by the queuing system for different purposes and for different resources. So for example, on Mahti, I will show you how you can get this information in a minute, but on Mahti, you have a GPU, a small partition, interactive partition, and a small partition. The partitions, the nodes that you can get access with GPU are started with this GPU thing. So you can have GPU small, GPU large, and GPU medium. And then there are some limitations. So for example, in GPU small, you cannot request more than 2 GPUs per node. But if you use GPU medium, you cannot use less than 4 GPUs per node. So it really depends. And with this free academic license, you don't have access to the large GPU partitions. So for that, you need to pay, okay? Through Jupyter Notebook, you have access to this GPU small, but if you connect through SSH, you have access also to GPU medium as well, okay? An interactive partition gives you access to a system with a small amount of hardware, but you can use it interactively, right? Then you can also get a portion of GPU. I will show you also how you can connect to these interactive sessions. And the small partition doesn't have the GPU, but you have access to a number of CPU nodes. How many CPU nodes and that kind of information you should get using a Slurm that I will show you today. So assume we want to get a partition with GPU, then you should select the number of CPU cores. So if you use a GPU partition, you cannot choose more than 4 CPU cores. So I set it to 4. You can actually increase it, but it gives you an error. Then the amount of memory, storage, things like that. And here, you should select the Python environment that you want to start with, right? This Python data environment creates a Python environment for you with some pre-installed Python packages like scikit-learn, things like that, matplotlib. Then you have other environments as well, but if you want to work with machine learning, you can use PyTorch or TensorFlow in this case. And you can also add your own packages there as well. So I select PyTorch here. Then you can select the version of PyTorch that you want to use. Then you launch it. It takes, I don't know, about a minute to activate the notebook for it. Okay. So in this current session, you have access to this Jupyter notebook about 4 hours. You can also request to extend this time. All right.
Can I request it during the session?
Yes. Then you connect to the Jupyter. Or I don't know, have a notebook here. So let's test if we have access to GPU. So just import Torch. Then torch.CUDA. That's
And
true.
Teresa, could you perhaps like share the screen?
Sorry? Ah, okay. All right. Sorry for that. Can you see it now? Okay. All right. So now we have CUDA available because we have a GPU now. Then it's true. So you can also interactively, I think, run this NVIDIA SMI, which gives you the information about your GPU that you have available. So now you have access to this NVIDIA 800 GPU. So you can get some information about the driver version, about the CUDA version, and some other things, probably the memory as well. So these kind of things you can get from this NVIDIA SMI. Then you can write your Python application, like PyTorch or anything you want. Is that clear? All right.
Is this Mahti?
This is Mahti, yeah. All right, so let's stop working with this web interface and let's see what actually we can do with the system through the command line interface. So I just try to close this connection. And if you don't use the system, make sure that you deallocate the resources that you got. All right. All right, so now let's open terminal. So I'm going to show you some basic commands, and then I show you how you can connect your VS Code and connect to the system through VS Code and submit some jobs. Okay. So it's kind of hard for me to see there. So let's see.
You cannot like, for instance, like duplicate it.
Yes, I can mirror it, but it's going to be a lot of things going on. Let's see. Okay. Now I can see myself. All right, so okay, so these are the things that I prepared. Okay, so let's see how we can work with this. So the first thing that you need to do is to connect to the system, right? So you can use this SSH. And in my case, my username is this one, and then I connect to mahti.csc.fit, right? If you have set up your SSH keys and everything, so you just get a prompt for entering your password, and then you ring. Okay. I usually use my custom shell, which is ZSH. So you can also install your own custom shell, and then you're here. Right? So now I am in Mahti, the login node of Mahti, not the compute node. All right. So let's see what we want to do. So the first thing that you need to know is something called modules or the module system. Basically, in HPC environments in computer clusters, you have a lot of users that using the system at the same time, which means each user needs like different tools, different compilers, different version of like utilities, things like that. And this can be quite messy if you don't manage these software dependencies. And for that, in HPC systems, something called moduling system or modules is used. So this is an abstract term, but like concretely, this CSC or this Mahti system uses the module system that is used is called M mode. So it's a L mode application, right? So what a module does is to manage the software dependencies for you in a way that's kind of separate from users to users. So for example, if you run this command, module list, you see the software like utilities that currently is activated on this environment for my user. So I have access to GCC now, OpenMPI, OpenBLAS, CSC tools, and some other things. So if I need another version of GCC, so let's say I want GCC 12, not 11. Using modules, I can deactivate this one and activate the other one, right? So for example, assume we want to have access to Python, right? So I can search all the software installed on this system and see what kind of Python environments are installed there, right? So then you can do it with modules as well. So if you want a software dependency like CMake, any compiler, CUDA compilers, any libraries, I don't know, whatever you need to develop your applications, then you should check with modules and see if the utility that you want is available there. If it was not available, you can also install it yourself. So let's make some examples. So as I said, this module lists the currently available ones for your machine. And if you want to search what modules are like the module that you're looking for, you should use this module spider command. So usually module spider gives you everything that is available there. So all of these things, most of them are command line programs, right? Like Emacs, like FFT, like things like that. So if you want to search for a specific utility, you should use module spider. For example, let's say I'm looking for Python. Module spider Python. Then you can see different version of Python available here. So if you want, you can use any of these ones, any of these Python versions. Is that clear, this module? All right. So if you want to know what utility is doing what, you can use this module help. So let's run this for this utility, like module help, the name of the and then it gives you some information about this current module, like for a collection of popular data analytics for machine learning and things like that. All right. So let's see how we can load a module. And by loading, because this module system, this L mode, works with environment variables of the operating system. So when you load a module, it manipulates the environment variables, usually the path environment variable, and this the environment variable for this dynamic linking. Then it activates, it gives you access to that executable, right? So this is how it works internally. But for activation, you use this module load, and then I want to use this Python data 2.8. Then it loads the module for you. Then if you run Python version, it should give you. So you get Python 3.8. So if you want to know what Python packages are already installed in this Python environment, you should use this pip freeze. And it gives you all of the Python packages installed within this Python environment. So you can see you have like scikit-learn, Ray, and Qt, things like that. But usually, like PyTorch is not here. Okay. Now assume you decided not to use this Python version, right? You want to use PyTorch, for example. And so what you do, you need to unload this Python module. Same as before, module, unload, then the Python version that I activate. Then you don't have it anymore. What if I want to work with PyTorch? Then I don't know if I have access to PyTorch, so I search for it. What was the command for searching for a package? Spider, then PyTorch. Then I have different version of PyTorch, right? Then I can activate it easily, whatever I want. Okay. All right. Something that is important about module is that they work based on a hierarchy system. So for example, some like components, like, I don't know, not PyTorch, but something like CUDA, they might depend on other software as well. So let me show you as an example. So assume I want to use CUDA to compile a CUDA program. What was the compiler name in NVCC, right? So if I run it, I don't have access to NVCC. It's not in my path, operating system path, right? So how can I check if a version of CUDA is available in this machine? Spider. Module, Spider, then CUDA, right? Then it gives you different version of CUDA, 11 and so forth, and so on. So let's check if I want to work with this CUDA 12.6. How can I activate it? Module, load, and then CUDA. You can use also your tab to get different suggestions. CUDA 12.6.1. Let's see if it loads. It doesn't. Why? Sorry, 0.0.
No, 0.5.
Yeah, I just wrote something wrong. Okay. So it gives me an error, right? So let's see how can I activate that. So for that, you should use this module spider and then the module name. Then it gives you the dependencies that you need to load before loading the actual CUDA version. You see? Because this version of CUDA works with GCC 10, but I have GCC 11 activated on this machine. So how can I solve this problem? Okay. So how can I know what GCC I have? Module what? What? I want to know what GCC is currently activated. Yes, but from the modules. The first command, what was it? You can also see there's a cheat list here. Right. Module list. So how to unload it? Module unload GCC 11.20. And then I have some other problems apparently. Or probably I used the wrong thing. Oh, unload, sorry. So it's now unloaded. And it also unloads the dependencies of GCC, right? So now, what was the version of GCC that I needed for CUDA? It was GCC, let me find it, this one, right? Okay, so I load it first. right? Then I try CUDA again. So it's done. Okay. So for some specific utilities, you need some dependencies that you need to activate before that. So now let's check if NVCC is available. So it's there now, right? It's on my path. I don't have any CUDA file now to compile. Questions? Okay. All right. So this module thing is quite important. So if you remember in the Jupyter notebook, when you were selecting the Python environment, you're basically selecting the module, right? All right. So enough about the command line. So now let's get our hand dirty and work with some real code. So usually I prefer using this VS Code. In order to work with the system, in order to integrate the this login node into this, you should install an extension which is called SSH. So if you open your VS Code and search the extensions for the SSH, you get remote-SSH extension. So try to install it now. Okay. And when you install the SSH, in the left down corner here, you'll see this icon.
Sorry, is the session recorded?
Yes. You see this icon, you click on it, and then you see this connect to host. If it's the first time for you that using this, there is something called add a new host. So you add the host, and the host is the address of this, your username, @Mahti or something, .csc.fi. Okay. So in my case, I have access to Mahti and Pufti, so I use this Mahti. Then it gives you a new window. Then you need to enter your password. The same password that you use to connect to the system through shell. And then your VS Code should be connected somehow. All right. So I'm now there. Then you can open a terminal in your VS Code. Let me start my ZSH. All right. So essentially, I have now the same thing, but it's integrated into my VS Code environment. All right. So now I have created a folder on my local user to run some jobs here. All right. So let's see what we can actually do with this. No questions so far?
The SSH command, well, when adding is with my username, right?
Yes.
Username.
Username @ like the mahti.csc.v. All right. In order to use the system using this Slurm and the batch system and everything, something that is important for expert users at least is to know what kind of program they want to run on the system. So let me ask you a question. Assume I have a serial program, right, that takes 2 seconds. On my laptop. It's a serial program, so I don't use any parallelism in it. right? So now I run it on Mahti with 180,000 cores. Is it going to be faster or not? Depends on what. So my code is serialized, completely serial. Why? Not technically, why? Okay, but because it is using only a single thread on a core. So even though you're using a supercomputer, you might be even slower, because usually when it comes to parallelism, as we discussed in the first lecture, you have a lot of CPUs, but the clock frequency might be smaller than the serial computers. So it's very important to know what kind of program you are running on these machines and how fit your program is into the infrastructure and what kind of infrastructure you are requesting based on your program. Things might be kind of abstract, I'm saying now, but the main thing that you need to know is the different type of parallelism, right? What kind of parallelism do we have? In general, we have shared memory, right? And distributed memory. Okay? When it comes to, you don't have another marker, right?
There's another one there.
This one doesn't work. But anyway.
No, I can go.
No, I can go, no problem. But just tell me where it is.
No, but I.
Okay. So when it comes to shared memory, how many nodes in the cluster we need to allocate? Assume I have a program with 10 threads. Okay? How many nodes in the cluster should I use for this program that uses 10 threads? Just one, of course. So if you use a shared memory program and then you allocate hundreds of nodes on the cluster, it doesn't really work well, because you have different threads and you need to access only one node to run this application. So it really depends on this shared memory, distributed memory as well. But if you have a distributed memory program, we haven't talked about this in the class, so it's gonna be the topic of our next lecture. But in this case, you have different programs running on different machines. And different machines have their own CPUs, their own GPUs, their own memory, and things like that, right? So in this case, you can allocate more nodes, right? More than one nodes. And we also can have a hybrid version, distributed plus shared. In this case, I need to set up my program and also my request to the system to give me enough resources for the number of threads that I have in my shared program and also the number of processes that I have in the distributed part of my program. Is it clear? Okay. So now I show you how to run different kind of program with different kind of parallelism, from serialized to completely distributed with single GPU or multiple GPUs on the system. Okay. All right, so let's see how we can run a serial program on the compute nodes. Now I would like to ask you another question. So what happens if I compile this program and run it in the command line here? It is serial, yes, but where it is being run? Is it running on the compute node or the login node? The login node, because you don't have access to the compute node directly. This shell is the shell of my login node. So if you compile it and run it here, you're just messing up the system, right? So don't do that. You can do it for debugging things, testing things, but for the actual execution, you shouldn't use this login node.
Like, is it okay for compilation running in the node?
Yes.
Or...
You can thank you very much. You can compile your program here and running on the login node, or you can set up this so-called batch script file that we are going to talk about to compile it on the compute node.
How will you compile it? Are you using the same compiler?
Yes.
The same dependencies. But it has to be managed.
Yes, so you can use also modules and everything here as well. So I will show you in a minute. All right, so this is a very simple serial program. It just implements the sum for an array, an average, I guess. So it's yes, it's compute an average. So I just wanted to have a simple example. So let's first compile it here. How can I compile this? Come on. Is it a GPU program? So why should I use NVCC? It's a GCC, isn't it?
And then the source file.
Oh. I call it serial app. Right. So now I have this serial app here. I can run it here. It's a small program that doesn't really matter, right? All right. So for running an application on a compute node or a set of compute nodes, you will write something called a batch script. The batch script is responsible for stating the requirements that you need for this application, like the number of cores, number of nodes, things like that. You will see it. And then you submit your batch script into the Slurm or the queuing system, and then you wait for the execution. So this is the basic flow. But I think I wanted also to talk about this as well. All right, okay, let me see. So I wrote a batch script for the serial program. So it's a shell script. So in the first line, you just select your shell. So I'm using bash to execute this. And then you use this hash s batch, like that is identified by slurm. So all of the lines should have this hash batch, okay? So in the first line, you have this variable called --job-name, which is only an arbitrary name for your program. Then you have to provide, especially in CSC, probably not other HPC environment, you need to specify the account variable. You need to set it up. And for that, you need to use your project ID. How we can get the project ID? In CSC, you have some tools in the command line that tells you some information about the project and things like that. It is called CSC-projects. So if you run it, you see different projects. So for example, this project is like HPC workshop, and then this project has an ID that you can see here, right? Then you should use this ID in the account part. Otherwise, you get authentication and authorization error, right? Okay. So these two lines are quite important. So the name of the job and also the project ID. Then you need to select the partition. What was the partition? A logical set of nodes for some specific purposes, right? So can I write anything I want here? No, because I really need to know what partitions are available on the system. The name of the partitions and the information of the partition on Mahti and Puhti and Lumi are different. So they use different kind of partitioning system. So you can use the command called sinfo that gives you a very messy version of this information about the partition. So for example, here I have columns, like partition, avail, time limit, node, the state, and node list. The first one is the name of the partition. So this is we have 4 large partitions, right? Then you can see also if they are available, if they are under maintenance, things like that. And someone tells me, is it a CPU partition or GPU partition?
CPU probably.
The GPU partitions, as I mentioned, start with the GPU. So you have GPU large, GPU medium, GPU small. So I have a large partition, I have medium partition. If you see a star here, it means that it's the default partition. So if you don't state the partition, by default, it chooses the medium CPU one for you. Then you can see also the list of nodes here. These are like node IDs. And if it starts with C, you see that like these are CPU nodes. So this is another way of understanding the partition information. Then I scroll down, I can see GPU partitions here. So I have GPU small partition and 2 GPU medium partition.
What are the GCs?
Sorry?
GC?
Which one? Oh, this one.
Uh-huh.
I have no idea. So if you want to use like your GPU, you should allocate these GPU partitions. All right. Then you can see like different information. But you can also further summarize this information if you use sinfo-s. Right? It kind of summarizes this thing for you. But here you get some important information with the nodes. Let me highlight it for the online guys. Here. So this information about nodes is kind of important if you want to allocate some nodes. The first number, A, is the available, it's the forgot that. It's allocated. So it's the number of allocated node in this partition, right? The second one is the idle nodes. The third one is offline nodes. And the last one is the total number of nodes. So now we have, like in this large partition, we have 1,332 nodes, and 320 of them are allocated. So it's not a good partition, basically. It's quite crowded now. So you have no node available at the moment in this partition. So if you submit a job to this partition, you probably need to wait a long time. Like for the small partition, you have like this information. So then you can check what kind of partition you want to use.
And so you said you have access to all of the partitions, right?
Yes. The large partitions you usually don't have access.
So do we get the information with this command that which partition we have access to?
No, all of the partitions. Yeah. So for example, if I run my job for a large partition, I get an error. That
The only way to figure that out is to
not
check it in user.
The best way to check is to read the documentation to see which partition is available for your user and what are the limitations. Okay. So now I know that I have a small partition, which is in this case a CPU partition. Then I can provide the maximum time limit that my job can run on this system. Then you have to provide something called mem per CPU. In a Slurm in general, a CPU term is not like CPU in hardware perspective. It's a CPU core, which means this is the amount of memory that you want to allocate per CPU core. So here I'm using only one CPU core because I didn't say anything about the CPU cores. And I get 2 gigabytes of memory per CPU core. Okay. Again, in a small partition, you are kind of limited. You cannot really use like 200 gigabytes of memory. It gives you some error. So the last one is about the I/O thing. Because your code, if you think about it, is not run on the login node. So you don't have your code your code is run on compute node, right? So you don't have access to the console of the compute nodes because you have the console of the login node. So you have to provide the output, and you can have a file or something like that, that the output of your program is written into this file, like in this case, serial.txt, right? And then it copies this file into my current directory. It doesn't show you anything on the screen. Your job is submitted, it is run on the compute node, the result is written into this serial.txt file, and then you can see the file here after your job is done.
So you just have to specify the name path, the name and the path will be.
No. If you say nothing about the path, it will be in the current directory. If you want to like have it in another part, you have to specify the absolute path.
Okay.
Right? But we usually don't do this in practice. In practice, CSC gives you a specific partition on the hard drive, which is called the scratch partition. It gives you 1 terabyte of space to store everything that you want. But this is only for testing purposes.
Okay.
All right. So let me open my browser here to show you how you can see the status of your job, both in command line and also in the web interface. So in the web interface, after you logged in, you see these jobs here, right? If you click on it, you see the active jobs. So currently I don't have any access, any active job, right? So what I'm trying to do now is to submit this job and wait for this execution. By the way, I just forgot to mention that. Lastly, you need to use this srun command from the Slurm to run your executable, right? And my executable is serial app. So now assume you want to compile the code on the compute node. So you write the compiler command here. You want to active some module, you write it here. So everything you write here as a command line program, as a command line like script, it is run on the compute node. Okay? What you write here is run on the login node. What you write here is run on the compute node.
Do I have to add srun at the beginning of each command, or you're just?
No, srun is for the executing things.
Okay.
Only when you want to execute your executable. Make sure that you have your executable available, either here or on the compute node.
And do we have to load modules like the bash script?
If it's needed, yes. So I assume I want to compile my CUDA program here on the login node. There I should load CUDA before the compilation and things like that. So for submitting your job, you just need to use this sbatch command, followed by the name of your script, run serial. Then your job is submitted, and if you refresh here, come on, you should see your job here in the right. So because my job was quite like simple, I didn't need a lot of resources, so it completed very fast. Right? So my job is completed now. So then you can see some information about your job, right? So this is how you check it using the interface. And here you can use this sq-me to see your currently submitted jobs, and it's a status. So for longer jobs, when I will show you. So is that clear, this job submission? So you write the batch script. Again, it depends on your program, what kind of parallelism you're using. Is it serial, is it parallel, whatever it is. You write your batch script, then you submit it using sbatch, followed by the name of your batch script. And then you can see the status based on the web interface or based on the command line. Okay, so if I now check my current directory, I see a serial.txt file that gives me the result of my program.
Sorry, do the compute nodes also have console?
They have console, but you don't have access to that. Through the web interface, you can get connected to one of the compute nodes. And there's also something called interactive session that you can also get access to one of the compute nodes, but with a portion of GPU, not the whole thing. But if you want to utilize the whole hardware resource, you should always submit your program using jobs. All right? Okay, so the next example is a shared memory program, which I wrote with OpenMP. So in this shared memory program, it's just a hello world program. So I just include OpenMP. And here in this pragma OMP parallel section, I spawn the threads. And by default, OpenMP like launches the threads available on your hardware. So I get the thread ID and the number of threads and just print them here. Okay. How can I compile this OpenMP code? GCC.
Same way that just have to specify the open
Yes. What was that from?
you see the name of the file and main out. That's
Yes, but I have to specify a flag.
the number of threads.
No.
What is the main?
F OpenMP.
I think that's just on Linux, right? Not
Yeah.
on Mac.
Yes. On Mac you have the same thing, but you need to specify the absolute address of the GCC because CLang doesn't have OpenMP already there. So GCC F OpenMP, then main OpenMP. What's the problem here? Oh, I just use this a different thing. All right. So now that I have my OpenMP executable, right? So let's run it on the login node. Where is it? OMP. Am I here? All right. So now I have 22 threads on this login node, right? From 0 to 22, 23 threads. Okay? So from 0 to 21, sorry, 22 threads. So let's run it on a compute node. How many nodes should I request for this OpenMP application? We just talked about that.
One.
Only one because it's a shared memory program, right? So let me show you the batch script. Run OpenMP. It's a little bit more complicated than a serial program, but it's still simple. So again, you need to specify the job name, which is in my case shared memory program. Then you have to specify the project ID with this. Then the partition name. I use CPU partition because I don't have any GPU code involved, right? Then you should specify the number of nodes with this dash nodes, 1. So I just allocate 1 node. Then you have to specify the number of tasks per node. In HPC application, a task is a process, right? So when you have a multi-threaded code, multi-threaded application, all the threads are like living within a process, right? So because I have a multi-threaded program, then I have a one process basically program, but with multiple threads, which means I have one task per node. So I have one node and one task per node, one process per node. So that's why I wrote this n task per node equals 1, right? Then you have to specify the number of tasks, which is 1 in this case. But here is a trick. You should be always careful to be, like this, the number of tasks should match the task per node and the number of nodes, right? Is it clear or not? So you cannot say I have one node and I have, I don't know. I have, I don't know. Let me see an example.
So you cannot run more than one process.
Yeah. No. You can run more process per node, but the number of tasks should match the number of nodes and the number of tasks per node. I will let you know if I found the example, but it can really happen in practice. So here it is a fit, right? We have one node and we have one task, and I have one task per node. So everything is okay. So then you should specify the number of CPUs per task. So if a task is a process, then the number of CPUs per task is a number of cores that your process has access to, right? The hardware threads that as we discussed. So I use, for example, in this case, 40 hardware threads, right? Because in a Slurm, as I said, CPU means core, not the actual chip. Then I allocate 2 gigabytes of memory per core, which is too much in this case. And then I write my output in this omp.txt, right? So if you remember, in OpenMP, I could specify the number of threads that OpenMP uses with this OMP num threads. So this line, this command is executed on the compute node, right? So I want to use the exact number of hardware threads that I have available on the compute node. So how many I have? I have 40. How can I define it? Using this CPU per task, right? So there is an environment variable in a Slurm that you can define, a Slurm CPU per task that gives you this 40. So I want to use as the number of hardware threads that I have in the compute node. Then I run my application. Clear?
Yes.
So now let's submit it and track its status. Still, it is one node application, so it really doesn't take so much. So how could I submit the job? Dispatch run omp.h. It is
And the number of cores be different from what the requested.
usually no. It depends. Of course, OpenMP can change the number of cores, but not more than the one that you allocated. So I submitted the job. Now, if you refresh here, it should be complete very fast. Yes. So it is already completed, right? So if you open this omp.txt, is it here? You can also refresh here. This code.
Not the OMP.
Only the OMP.
Oh, okay. All right. So now you can see we have 4 threads, 40 threads, not 22, because we allocated 40 hardware threads. All right. Apart from checking the status of your job, you can also see what's the status of your complete jobs. So let me see here in my notes. You can use this yes, SACC thing. Yes, no, okay. So if you use this SACC command, it gives you the status of all completed jobs on this machine, not necessarily in your project, but all the projects. So then if I have my job ID, which you can get using the interface here, this is my job ID. I can run this command -j followed by my job ID, and I get the information about my job. So for example, here it says that I allocated 40 CPUs and the job state is complete. And then there's also another command within a Slurm. It's called ceph, followed by your job ID. And it gives you how efficient your, it gives you some information about the efficiency of your program, like the wall clock time, like the efficiency in percentage and things like that, how many nodes and CPUs you're using, things like that. All right. So easy so far. So the next one that I'm going to show you is how to run jobs on GPUs, multiple GPUs or single GPUs. So first I will show you a CUDA program, which is the very first program that you want to write when you're working with CUDA, which is about getting detailed information about your GPU using CUDA. So I didn't talk about this in the class, so I go through the code a little bit, show you how you can get different information from the GPU. Okay, so here you define a variable called device count, which gives you the number of devices available on a node, right? Then you can use this CUDA get device count, and then you pass in the address of this device count, and it gives you the number of GPUs available on your system. Then you check for error and these kind of things. Then you loop through the number of devices. You can define a variable called in the type of CUDA device properties or CUDA device prop. And then you get the properties of your GPU using CUDA get device properties. And you pass in the address of this variable and the number of the index of the GPU. So in this case, I want the information of the 0th GPU, the first one. And then you can get different information like the GPU name, the major version, the total global memory, I don't know, how many registers I have per block, how many threads I have per block, number of streaming multiprocessors, the clock rate, this kind of information. So I use this function, CUDA get device properties, to get the properties, and then I just print them out. So let's try it on the login node first. Let's see what happens here. First, somebody tells me, how can I compile this?
NVCC.
Finally. So NVCC, but I don't have it here.
Oh.
So what should I do now?
So,
Module, spider first, CUDA. So for simplicity, I use this CUDA 11 here, right? I don't want to manage those dependencies, things like that. Module, load this. So now I have NVCC available. So let's compile it. NVCC main.cu-o GPU info. All right, so I have a GPU info executable now here. So let's run it and see that it doesn't work. GPU info. Why it does not work? This error is nonsense basically, but what it doesn't work?
I think the device count executable.
No.
Do we have a GPU?
No, of course. We don't have a GPU on the login node. That's why it does not work, right? So I should allocate a compute node that has a GPU, right? And then execute this code there, not on my login node.
So for this, I work with me to send as a batch first.
Yes. So you need to write a batch job first. Let's see how we can write it. Okay, single GPU batch one, yes.
For testing, you could also use like an interactive session or something.
Yes, but we haven't talked about that.
Yeah.
I'm not sure if we have time, but anyway. So again, I write my job name, single GPU, the project ID, and things like that. Then the partition, I use this GPU small. How can I get the partition name? With sinfo, the command. So how many tasks do I have? It's still one process, right? And I just here use four core per process, like doesn't really matter here. The memory doesn't really matter, but here the important part is GRES, which stands for general resources. Here you should know, you should specify the GPU, and then the model of the GPU. On Mahti we have 100 GPU. So if it was PuTTY, you should use V100 because in PuTTY they have V100. In Lumi, they don't have NVIDIA GPUs, so there's another name, right? And here, you specify the number of GPU per node, right? On Mahti, each GPU node has 4 GPUs, right? But when you use a small partition, you can only use 2 GPU per node. Is that clear? Not more than 2 GPUs on the small partition of Mahti. If you use different HPC environment, it might be different.
Sure, I maybe I missed it, but our code will use both GPUs.
Yes, you will see the result. And then you have this output file.
Okay.
All right, let's submit it. It might take a little bit of time because you are now want to access GPUs. Oh, where does it go?
This job can also have more overhead than simple CPU.
Yes, because you don't have a lot of GPUs there. Okay, batch. One single GPU. So it's submitted now.
And we didn't need to load the models that we loaded in the loading. No,
What model?
the GC.
Oh, the module. No, because you want only to execute now the code. You don't want to compile it. For the execution, you just need to have a GPU, right? So it was quite fast. Probably the system is not that crowded now. So if I open this single GPU.txt file, if it is there, can you see it? Okay. So now you see we have 2 devices, device 0 and device 1. So it's interesting because this part comes from the first GPU, and this part comes from the second GPU, right? So then you can see the information of the GPU, like the compute capability. We haven't talked about this, and we won't. The shared memory, like the registers, warp size, maximum thread per block, how many dimensions we can have, this kind of thing. It means that our CUDA program actually ran on the GPU. And this is for the second device. Right? So you can now run any CUDA program. At least for the next homework assignment, you can run it here or your projects. Okay, questions? All right. Now, what if we want to use multiple GPUs? So I still run the same executable code. So here, what I did in this code, so I'm using the GPU medium, not GPU small, because I want to use 4 GPUs per node, right? I define 2 tasks. It really doesn't matter at the moment. So the important thing here is I am using like 2 nodes, right? And I'm using 4 GPU per node, which is 8 GPUs in total. Okay. This takes around 2 hours or something to be executed. At least it took it yesterday. So it's a good example to show you this queue system status, things like that. So let me submit it. Do you understand this, the code? It's quite simple. So, all right, so let me submit it as batch. What was the name? Run multiple GPU. So it's now submitted. So it takes a lot of time. So now you see the status is queued. So it's not, now it's in the queue. And the state is pending. So now it means that you need to wait for the system resources to be freed by other users, and then a Slurm will like put your executable in the compute node. So now I can explain something else here. So let me check the queue using command line. You can use sq --me. So now you have this information. So this is your job ID, the partition we are using, this GPU medium, the name, the user, the status is pending, time, the number of nodes. right? So if you want to know when your job is done, you always need to like use this command all the time. But there's a small catch here. You can use this watch utility, and then you put this into a string. Then it updates this, it runs this command after 2 seconds. So then you have like kind of not real time, but continuous information. Or you can also refresh here, check what's the status. It's still in the queue, so I think it's going to be in the queue for a long time. All right, so let me see if I have more things about this job submission. Well, there's a there's an example about MPI. We didn't talk about that, so we're going to talk about this next week. But let me show you how you can submit MPI jobs. MPI actually is for distributed program systems. So usually you have multiple nodes and you run different programs on the multiple nodes. Usually in machine learning, at least, you use a pattern called SPMD, single program, multiple data. If you remember, we had something called SIMD. Right? In SIMD, you have single instruction, multiple data. When you have a lot of instructions, you can form a thread, right? So in NVIDIA, like when you use GPUs, you have something called TMD. No, sorry. I forgot the term. Yes. SPMT. Single program, multiple thread. But here you have SPMD. Single program, multiple data, which means you can now run a multi-threaded program, not necessarily only one thread, on a single machine, and you can have the exact instance of the same program on another machine. So it's quite in a the highest level of parallelism hierarchy. We talk about that later. And then you can have communications between those kind of things. For example, in machine learning, assume you have a huge data set, right? You can kind of divide your huge data set into 4 partitions. So each partition, like P1, let's say 2, just for simplicity. You have 2 partitions, like 500 gigabytes or something. So you store this partition in one compute node. You store this partition on another compute node. Then you have a machine learning algorithm, right? Some of this algorithm in parallel works on this partition, another works on this partition, and then they send the data to each other to train the model. So this is called distributed data parallel training. Okay? Which you do it using MPI and distributed memory programming. So now I want to show you how you can submit these kind of jobs into Slurm, and also the hybrid jobs, MPI and OpenMP together. Okay, let me open a very simple MPI application. I won't go deeply through the code because you're going to learn it later, but I just need to initialize the MPI library. Then I want to know the total number of nodes here, and then like the name of the process that I'm running, these kind of things. It doesn't really matter at the moment. So let's see how we can run it. So I have this run MPI script. Again, I should have my name, like the account type, the partition. I'm using CPU because like MPI is for connecting between CPUs. If you have GPUs that you want to have a communication between them, you should use a library called NCCL, NVIDIA Collective Communication Library, which is only for GPUs, or something called CUDA aware MPI. These are just for your references, so I'm not talking about these things. All right, but at the moment I just use CPUs, different nodes only with CPUs. So I choose this medium partition. So now I can allocate 20 nodes, which means 20 single computers, right? And I have one task per node, which means only one process is running per node. And then I have 20 tasks. So now, assume you have 15 tasks. And then you allocated 20 nodes. That's the example that I was looking for. Now it doesn't really match. You have 20 nodes, but you have 15 tasks. You can really divide it between 20 nodes.
But you could technically have more than one task per
You can.
node, right?
Yes. But the number of tasks and the number of nodes should really match. And then I allocate like 1 GB of memory per CPU core. And then I write the result here. So I don't submit this job, just I wanted to show you how you can submit. And if you have both MPI and OpenMP, the only thing that you need to add is this CPU per task, right? So let's go through it. So I have allocated this medium partition, right? I have requested 5 nodes, and between each node, I want to have 10 hardware threads for the CPUs, right? And this should match really your OpenMP program as well. Then the number of tasks per CPU per node is 1, right? So you have 5 processes. Then I allocate each process to a node, and each process can have up to 10 threads. From the software perspective and from the hardware perspective, you have 5 nodes and 10 CPU cores.
Yes, like using 2 levels of parallelism.
Yes. Then here I use this this line to make sure that the number of threads that OpenMP is using is the same number that I provide here as the number of hardware threads.